Hi everyone, let's talk about electrostatic interactions. And when we say electrostatic, what we mean is that, the word static is used for stationary objects and dynamic is used for moving objects. So when you say electrostatic, you mean electric charges that are basically at a location that you assign them to be and then they don't move from their location. So when you take two charged particles and put them in some distance r, so we call the distance between the two charges we take as r, and the first charge to be q1, then the second charge to be q2. So we're asking the question, how are they interacting? What is the force they apply to each other? So that is basically answered by what we call Coulomb's law. So the Coulomb's law tells us the magnitude of the charges by basically multiplying the constant, the Coulomb constant, which is in reality, it has more digits, but in 3 digits after the decimal point, it's 8.988. So for practical purposes, we use it to be 9 times 10 to the 9, but the simulation you will use for the lab is going to take it as this. So there might be some slight differences if you do the calculation, and I will show it at the end anyway. So again, for the mathematical purposes, I'm going to use it as 9 times 10 to the 9 Newton meter square over Coulomb square is the constant for this law, Coulomb's law. And you multiply the two charges that you're trying to find what is the force between them and divide it with the distance square. So it's the inverse square law, therefore the force between two electric charges basically diminish in a very short distances. So this is a short distance interaction between charges. So they need to be in very close vicinity to be able to apply any substantial force on each other. So the direction of the force, on the other hand, comes from the knowledge that like charges repel each other and unlike charges attract each other. So when you are given two positive charges or two negative charges, you know that they're going to repel each other. And so you tell that if Q1 is positive and Q2 is positive, then the Q2 is going to apply a force toward left on Q1, and Q1 is going to apply a force on Q2 toward right because they're repelling. Similarly, if they are negative. And if one is positive and one is negative, or vice versa, so they're going to attract each other, therefore the force between them is going to be like this. So the Q1 is going to apply a force on Q2 toward left because it's attracting it, and Q2, being negative in this situation, is going to apply a force on Q1 toward right because it attracts it again. So repulsive forces basically is shown like this, and the attractive forces are shown like this. So the direction of the force comes from this knowledge, and the magnitude of the force comes from Coulomb's law. And once again, the magnitude of the force that two charges apply onto each other is the same because the formula is the same for each other, right? K, Q1, Q2, and R doesn't change if you consider one or the other of the charge, but the direction depends on their being both positive, both negative, or positive and negative, or vice versa. So you basically use the fact that like charges repel each other and unlike charges attract each other to figure out in which direction a charge, a given specific charge, applies onto other charge. So let's take an example of 4 microcoulomb and 8 microcoulomb, and the charges in nature are really small in terms of magnitude. So they're mostly given in microcoulombs, and micro is a prefix of metric unit system. If you look at the table that we discussed at the first chapter, you will see micro as a prefix stands for 10 to the minus 6. So the conversion from microcoulomb to coulomb is basically replacing micro with 10 to the minus 6, just like you basically change 2 centimeter by using a centimeter. Centi prefix stands for 10 to the minus 2. So you change from centi to meter by replacing centi by substituting 10 to the minus 2. And I need to do this conversions because, as I had given you, the unit of the Coulomb's constant is Newton times meter square over Coulomb square. So basically you cannot use microcoulomb or centimeter in your calculation when you need to multiply it with a unit of meter and coulomb. So you need to convert them like this. So let's see how much force these 4 microcoulomb and 8 microcoulomb applies onto each other. So you substitute these numbers into our coulombs law, where you have, again, I'm using 9 times 10 to the 9 for practical purposes in my calculation for the K, the Coulomb constant. And the Q1 is 4 times 10 to the minus 6 because microcoulomb is 10 to the minus 6, and 8 times 10 to the minus 6 coulomb. Again, micro is 10 to the minus 6, and the distance is 2 centimeters, so it's 2 times 10 to the minus 2 meter square. So the distance is squared, so don't forget this. And I definitely advise you to do the squaring of the denominator at the very beginning, so that if you feed these numbers into your calculator, if you put a square at the very end without using, any parentheses, it's going to probably square the whole thing. And therefore, I really highly recommend you to do the square at the very beginning and write down the result here and use those numbers. Personally, what I do is I deal with the numbers first and the powers of 10 seconds as a whole, and then deal with the results and turn it into scientific notation. That's how I do it. But if you feed the whole thing into a calculator, probably it's going to give you a direct answer anyway. But that's how I do it. So I'm showing it this way. So I multiply 9, 4, 8, and divide it with 4 because 2 squared is 4. These are my numbers, and the powers of 10s I have is 10 to the minus 9, 10 to the minus 6, 10 to the minus 6, and in the denominator it's 10 to the minus 2 squared, which is 10 to the minus 4. So when you do this math, you get 72. When you do this math, you know that you need to add the powers of 10 when they are multiplied, and then subtract it if it is in the denominator. So it's 9 minus 6 minus 6 minus 4, right? So it's basically addition of what you have as a multiplication minus whatever you have in the denominator. So you get, this is minus 3 plus 4, so it's plus 1. So in a regular writing, it's 720 Newton. In the scientific notation, you know that you need to have actually one single non-zero number before the decimal point, so you need to carry your decimal point toward left twice, so you're going to write it as 7.20 times 10 to the 2 Newton. This is the scientific notation, and this is the regular notation, okay? So I'm going to show you the simulation with these numbers now, so you see the difference between using 9 times 10 to the 9 versus 8.988 for the K, because the simulation is using this whole number. It's actually longer than this. So the simulation is using the original K value. And so you will see that the simulation, if you put your 4 and 8 into the simulation and with the 2 centimeter distance, you will get 7.19 instead of 7.20. And once again, the direction of the force that Q1 applies onto Q2, because both is positive, is repulsive. I know that the Q1 is going to repel 8 toward right, and Q2 is going to repel 4 microcoulomb toward left. This is the repulsion, okay? So the direction of forces direction of the force Q1 is experiencing is toward left, direction of the force Q2 is experiencing, because of the existence of Q1 sitting 2 centimeters away from it, is toward right, because they repel each other. If one or the other is, if they're oppositely charged, if one is positive, the other is negative, then they would be attracting each other, and so you would basically reverse these directions. Because I gave you both positive. And by the way, you don't use being positive or negative in this formula. Formula doesn't care about being positive or negative. What you get basically is that mathematically use these numbers for your charges in your calculation. And then look at the picture. Are they having the same charges, like in terms of positive or positive and negative, or are they having unlike charges like positive and negative and positive? So again, the direction of the force is found by using this fact that like charges repel and unlike charges attract each other. And so by looking at the picture, you just figure out whether they are repelling, and then you put your arrows, and the simulation is going to be showing that too. So I'm going to show this example in another video in the simulation. Have a good day.